primero, buenas tardes. Gracias por acercarse al Salón Meridiano y gracias también a los que están conectados de manera virtual. Hoy vamos a continuar con el ciclo de seminarios que organiza la facultad y en esta oportunidad nos visita la doctora Ariana Dolfi. Bueno, Ariana obtuvo sus títulos de grado y máster en la Università Roma III, Italia, y posteriormente realizó su doctorado en la Swinburne University of Technology de Australia, bajo la dirección de Duncan Forbes. Actualmente es becaria postdoctoral de Decir, con lugar de trabajo en la Universidad de La Serena, en Chile, y sus trabajos previos se han enfocado en la formación y evolución de galaxias, contrastando propiedades observacionales con resultados de simulaciones cosmológicas y hidrodinámicas. El título de su charla de hoy es Perturbaciones morfológicas como trazador de la evolución galáctica y del entorno. Bienvenida y suerte.
Okay. Thank you. Thank you everyone for coming, and thank you very much for the opportunity to give a talk here. And I'm very much enjoying the stay here. And so, as you mentioned, today I would like to talk a bit about the project that I've been working on while in Chile, in La Serena, about the morphological perturbations as a tracer of galaxy evolution. And no sé si... Sí. Thank you. When talking about morphological perturbation, in particular, I'm here focusing on lopsidedness, which refers to an asymmetry in the mass and light distribution of these galaxies, where actually one side of the disk is more extended than the opposite side. And why is this perturbation interesting? Well, because they are observed both in the local universe, and there are also no observations at higher redshifts. And because since this perturbation results in a shift of the disk's center of mass with respect to the density cusps, this introduces torques throughout the disk, which can affect the cyclic evolution of the disk, such as in particular its dynamics, the star formation activity, and also the feeding of the central supermassive black hole. And among the processes, there are several mechanisms that have been proposed to as region of lopsidedness, and the most common one typically involve in external perturbations like flyby or a tunneling correction, a correction of gas feeding asymmetrically more one side than the opposite one, or the response of a disk to a previously perturbed dark matter halo. And so in this project, so we've used the illustrious TNG simulations, in particular the TNG50 simulations, to study this type of perturbation. And so what we did was selecting a sample of disk galaxies at redshift 0. Here you can see the stellar mass distribution between 10 to the 9, 10 to the 11.5 roughly. And this is the green line here shows the comparison with the stellar mass distribution from an observational paper where they've studied the lopsidedness in the SDSS survey. And well, due to the TNG50 simulation are higher resolution simulations, but the cosmological volume is it's smaller. So they only include one cluster environment, and galaxy groups up to Fornax-like cluster environments. One of the way to measure the lopsidedness perturbation is via Fourier transform. So by measuring the amplitude of the first Fourier mode in concentric radial annually. And here we see an example of a simulated galaxy from the NG50 simulation. And by measuring the A1 amplitude in like concentric radial annually, what we reconstruct is the A1 profile as a function of radius. And here you can see typical lopsided profile is typical profile of a lopsided galaxy, which has low A1 amplitude in the inner regions, and it increases as we reach the disk outskirts. And to quantify the global lopsidedness of the galaxy, then we take the average of A1 within a given radial range. And in previous observations, this radial range typically correspond to between 1.5 to 2.5 effective radii, or some observations from STSS were able to reach out to R90, so including 90% of the mass, where the outer radial range depends, of course, on the signal to noise of the observations. But as we see, like although the R9 can like capture the lopsided feature, like having deep observations will be ideal in order to fully capture the extent of the lopsided feature, since this is stronger a larger radii, so in the disk outskirts. And in fact, here we see that if we extend the measurements like out to, for example, the optical radius of the galaxy, we can probe the disk outskirts, and we find that if we use this radial range in the simulations, we've seen that if we use the radial range similar to observations, we recover similar fraction of lopsided galaxies. But when we reach out to the optical radius, we recover a much larger fraction of lopsided galaxies. And so once we quantify the lopsidedness in a sample of simulated galaxy, here we recover the A1 distribution. And as you can see, this is the median of the distribution is roughly around 0.1. And this is generally the lopsided threshold adopted to separate between lopsided galaxies, so with A1 greater than 0.1, and symmetric ones. And this is generally the median value that was found in like previous observational works. And it is now the threshold adopted to separate between lopsided and symmetric galaxies. And this again overplotted here screen is the comparison with the A1 distribution from the observations from the STSS survey from this previous work. And consistent with observation, we see that the A1 amplitude tends to decrease with increasing stellar mass. We're missing here in the simulations the lower mass galaxies, because we start from 9 greater than 10 to the 9. And in fact, when we look at the correlation between the lopsided amplitude with the local environment and the internal properties of the galaxies, we see that consistent with previous works, there is not. So we look at the correlation between the A1 amplitude with the number of nearest neighbors within the visual radius of the galaxy. And we see there is not a strong correlation with the local environments. But if we look at looking at the correlation between A1 with the internal properties of the galaxy, such as the photometric bulge to total ratio, we see that the galaxies that have lower bulge to total photometric ratio tend to be more strongly lopsided. And this is consistent with what we're finding, that the lopsided galaxies tend to have lower concentration, lower central stellar mass density, and because of this, they are more easily perturbed as a result of an external perturbation. And when we extend our sample selection at higher redshifts, up to redshift 2, we see that we continue to find like similar results. So there is here we see the correlation between 1 and the local environment, considering like the density of the 10 nearest neighbors. And we see there is only like very mild correlation, but there is a much stronger correlation when we look at the amplitude of the A1 with the central stellar mass density and the R90, so the disk extension. So the lopsided galaxies tend to be more tend to have more extended disk and be less centrally dense. And because of this, well, here I would like to mention like what that was done by a Master of Science student at the University of La Serena, which I had the opportunity to be part of. And what she did was selecting like a sample of these galaxies, ratio less than 0.5 in the TNG50 simulation. And she trained a like machine learning algorithm based on random forest to classify this sample of galaxies as lopsided and symmetric using only like the internal properties of the galaxies without prior information about the environment where they are located. So what she did was first use the Fourier transform to measure the A1 and classify galaxies as lopsided and symmetric. And later on, like in the random forest algorithm, and here we see the confusion matrix that she was able to. I mean, the algorithm was able to correctly classify the lopsided and symmetric galaxies with like 80% accuracy. And in the middle panel, she ran here she showed the feature importance, like which are the most important features used by the algorithm to classify the galaxy as a lopsided or symmetric. And the main like properties, they are the like central stellar mass density, the trazador parameter, which is a proxy of is a proxy of the like force exerted on the outer disk regions from the inner regions, and the star formation rate. And when in the left panel, it's also like featured that when using only observational parameters, so parameters that can be more easily recovered from observation, such as the central luminosity, the alpha light radius, and the star formation rate. So, so overall, we see that, I mean, this method could be while of course it could work as could provide a good like pre-classification of galaxies in like the upcoming multi-band photometric survey, like for example SST. And now going back to a sample of galaxies at redshift 0. An interesting result that we find is that when we look at the star formation history of present-day lopsided and symmetric galaxies, we see that they are characterized by distinct assembly history. So we see that while the symmetric galaxies have typically show a peak in the star formation star formation at early times, the lopsided galaxies have a more like gradual growth and assembly. And when we look at the cumulative fraction of stellar mass as a function of time, we see that the symmetric galaxies have typically assembled 50 and 80% of their stellar mass around 1.5 years earlier than the lopsided galaxies. Here we try to look also at the net accretion rate, the net gas accretion rate onto the disk of our galaxies, and using quantifying the net accretion rate using this expression, which is defined as basically that's the gas mass in the disk at a given snapshot minus the gas mass in the disk at the previous snapshot, plus the stellar mass that was formed in the disk during the given time interval. And we see that specifically, like in more recent times, the lopsided galaxies have generally experienced a higher net accretion rates onto the disk compared to the symmetric ones, and which might explain why the lopsided galaxies, so they may have experienced higher net gas accretion rates, which kept the star formation overall constant until more recent times and shaped a more gradual mass assembly. So from this project now, what follow-up that we would like to do, and we started, is we would like to look at this. We would like to verify these results that lopsided and symmetric galaxies have different star formation histories using the JPAS survey, which is survey characterized by 54 narrowband filters. So it allows for a stellar population study similar to IFU-like, and it is so. This project is currently ongoing in collaboration with the other JPAS members, and we are currently looking at the classification, how to classify lopsided and symmetric galaxies in the observations using the morfológicas. But the end goal will be to recover the star formation rates, the star formation histories of the galaxies in the observations to verify our theoretical predictions. And now another project that was working on was looking at the coupling between the asymmetries in stellar and H1 component. This is because the lopsidedness is not only observed in the stellar component, but it's also observed in the H1 morphology and kinematics. In particular, like in the kinematics, the lopsidedness in the kinematics appears as an asymmetry in the rotational velocity curve, where one side of the rotational velocity rises more steeply than the opposite side. And the combined study between stellar and H1 gas lopsidedness could provide important clues about not only the mechanism triggering lopsidedness, but also about the recent galactic evolutionary history. And this is because if, as we've seen before, if lopsided galaxies have indeed experienced higher net gas accretion rates, which could have triggered like the lopsidedness, then we would expect stronger asymmetries in the gas than in the stars. And while if it was instead the result of an external perturbations, we will expect a coherent response in both stars and gas, and also morphology and kinematics. But well, so far, most of the observational works have mainly focused on studying the lopsidedness either in the gas or in the stars, and so using many different radio ranges to quantify lopsidedness, and which makes it difficult, like to compare to study the correlation. And in the previous work here, they've used the TNG 100 simulations to look at the correlation between stellar and gas lopsidedness. In this case, the total gas, but they didn't find any strong correlation. Well, this could be due either to the measurements, which were more restricted to the inner regions, which may affect the lopsidedness measurement, or also the fact that the TNG 100 simulations are a bit lower resolution, so it's harder to resolve the outer regions of the disk. In this work, for this reason, we've used the Auriga simulations, and in particular the Auriga Superstars simulations, which they include they simulate a subsample of 9 Milky Way mass halos with a higher stellar resolution and with higher snapshot cadence. And the higher resolution allows to improve the visibility of features and structures within the disk and the halo, and the higher also, the better sampling of the gravitational potential and the snapshot cadence allows to better study how the different dynamical processes can affect the properties and structure of the disks. And here you can see an example of one simulated halo, and this is the stellar surface tightness, and in the density of the H1 gas, which we recover in the simulation, and the orange circles, they represent the radio range between 0.5 and 1 optical radius, which we use to quantify the lopsidedness. And both in the morphology and kinematics. And here you see the covered radial profile of this galaxy. We see that the A1 rises consistently both in stars and H1 gas. And here in the left panel, we look at the correlation between the stellar and H1 gas lopsidedness, and we see that there is in general a good correlation between the two tracers, and also the points here are colored by the central stellar mass density. And although there are a few exceptions, we see that the A1 amplitude tends to it's stronger for the galaxies with lower central stellar mass density, and increases as we move towards galaxies characterized by higher central stellar mass densities. And in the right panel, we show similar same as the left panel, but separating between the younger stellar component, less than 500 megayear, and the older stellar component. And we see that in the case of the old stars, we see that the correlation is again strong for with the H1 gas, suggesting that the two are dynamically coupled. but while the young stars are better tracing the asymmetries in the star-forming gas. And another another correlation that we find, more anti-correlation that we find, is when we look at the amplitude of the stellar, the density, the lopsidedness in the stellar density in the outer regions of the disk, and the bar strength in the inner regions. The bar strength in the inner region is quantified by measuring the amplitude of the m equals 2 Fourier mode within the 10 kiloparsec and taking the maximum value, similar as it was done in previous work. And again, we see that although there are some clear and outliers, and the majority of points they tend to lie in here in this over this line showing anti-correlation, where galaxies showing characterized by the more symmetric disks tend to have higher central stellar mass density, and low lopsidedness, while the galaxies characterized by the stronger lopsidedness tend to have low central stellar mass density and not develop bars. And this is likely the result of the strong correlation that there is between the lopsidedness bar and the internal properties of the galaxies. And okay, here we then quantify then the lopsidedness in the kinematics, and the lopsidedness in the kinematics. Well, here in the case of a phase-on radial velocity, because the lopsidedness, so it introduces non-circular motion within the galaxy, and they appear as a dipolar feature in a phase-on radial velocity map, where with one side we have inflow, so via negative VR, while on the opposite side show as an outflow, so positive radial velocity. And we quantify the kinematic lopsidedness of our galaxies in a similar way as done for the morphology within the outer region of the disk. And here we show the correlation between the kinematic and morphological A1 in the case of the stars and H1 gas. And while the correlations are more moderate compared to the correlation that we saw in the case of the morphological lopsidedness, we see there is a moderate correlation between the kinematic and morphological lopsidedness in the case of the stars, and in the case of the gas, although the H1 gas kinematics is always stronger compared to the morphological one, to the morphological lopsidedness. And we see, for example, that galaxies that tend to have a highest value of kinematic and morphological lopsidedness, which also generally have which are also generally lopsided in the stellar component. This suggests that more like a totally induced origin, while other galaxies which tend to show more lopsidedness only in the gas kinematics and only weakly in the morphology, they suggest more like gas expression in those lopsidedness. And here we, so to better understand this, we look here at the temporal evolution of the lopsidedness in the last 7 gigayears of the galaxy history. And so in this figure, so the main panel here, it shows the evolution of A1 in both stars and H1 gas. While in the bottom panel, we show the orbits of the most significant interacting and merging satellites, normalized by the virial radius of the galaxy, where the one virial radius is represented by the dashed line. And like the two galaxies which are currently lopsided at the present day, they in both these galaxies the lopsidedness was generated as a result of a previous interaction. We see, for example, in the case of AU25, we see that the rise in both stars and H1 can be associated to the close precentric passage of a satellite or a massive satellite galaxy. And while in case of these other galaxies that they do not develop any strong asymmetry in the stellar component, they only have at the present day, they only had like previously a strong asymmetry in the H1 gas, which was one case of the result of a gas-rich like satellite, like orbiting nearby the galaxies, and with during which this gas was stripped and accreted onto the main host. Or in the case of the AU18, that we do not find any significant interaction with any nearby satellite at early times. This might suggest that the accretion may come from a like filamentary structure. But we would like to, and this is something that now we would like to look at more in details by tracking the gas cells and to see to understand well the origin of this gas. And well, in this, so these are my conclusions. And so we've seen that it seems that lopsidedness is indeed like a tracer of the internal structure of galaxies and could be used as a powerful like diagnostic of the early galactic assembly history, and also like observations of the stellar and H1 gas lopsidedness could be a useful probe of triggering mechanism of lopsidedness. And as a next step that now we would like to investigate this like looking, because the lopsided seems that the lopsided galaxies have accreted more like gas. It might mean that they could be like located in like differential environments and that facilitate this gas accretion. And we would like to investigate this using the TNG simulations, which have a larger cosmological box. But we also like to investigate more the origin of the gas accretion, whether it occurs like the direction of the gas inflow using the Auriga simulations, and to investigate this more in details. And thank you.
Gracias, Ariana. Bueno, ahora el momento de las preguntas o comentarios. Si alguno quiere hacerlas, acerca al micrófono. Virtuales.
Next talk. One quick question is about if you think that past Asian activity might have some relevance in the evolution of the galaxies that were caused by the late accretion of us.
It could, yes, now that's interesting. I mean, it could be interesting, yes, to explore. We haven't looked at it yet. But yes, it could, yeah, this is something, yes, interesting. It will be interesting to explore. Yes.
Sorry, another thing. Do you think a lot of daylight galaxies, when they start to fall to a scale that gets to like, they are not the cases that you have analyzed here in Auriga, but when they start to fall, they suffer run pressure. I wonder if in an observational survey we should find that most of those lopsided galaxies are galaxies that are near the bigger radius, between 1 and 2 bigger radius, that cluster-like areas start to experience this compression.
I think, yes, I would expect, yes, that when the galaxy they start to fall, they experience more, they start experiencing the ramp pressure. That will be the moment to observe this feature. And there is actually, the interesting thing is that there is actually recent observational work, they found that they've analyzed the lopsidedness in the gas in H1 and in like 2 different group environments, and they've seen that in one group they found that they claim that there is a larger fraction of lopsided galaxies compared to another one, and which could it could suggest that there are differences, between the 2 groups. Maybe one group is more like there's more like interactions, or is more active in terms of interactions, or compared to the other group. So this could maybe be a tracer of the dynamical state of the group, and it is something, that will be interesting to investigate.
Respecto a uno y al otro de Fourier, es como una forma de mensurar estructuras, las barras.
Sí.
He intentado hacer eso en las esferoidales.
No.
Para ver si hay mucha diferencia entre las esferoidales y los discos.
De uno en las ciudades no, aún no lo hemos intentado. Podría ser algo interesante, sí. Sí, se espera que, como hay como trabajo en observacionales, donde sí un poco estudiaron eso, donde intentaron como ver igual esa simetría en galaxia más early type.
Gracias, Ariana.
Gracias.